Hello everyone, welcome to video 14. What we're going to dive into now is kind of the last portion of calculus and business calculus in general. So there's only one more video that we're going to see after this. And so it's going to be kind of cut short in terms of what we would normally see in class, and that's perfectly fine. So hopefully this will kind of convey the general idea and really kind of set us up for the main big concept of calculus, which is then continued in a Business Cal 2 course or a Calculus 2 course, all the way up through a Cal 3 course. So um, this will also be your final assessment piece over this topic. And so let's dive right in. So the objectives of this video is to essentially kind of look at the question of how do we find the area under a curve? All right, so we know how to find the area when I have solid straight edges, and we'll kind of see this in the first kind of question here. And then, but how do we do it if it's not straight, right? What if it's curved? How do I find the area of that? And then we want to learn about the notation, which is used to represent the exact area under a curve. And you can probably guess that is what is known as the definite integral, which you see in the title. All right, so to go ahead and start, the first topic is going to be the area problem. All right, and so the very first thing that you really need to kind of take away is that there is a problem. And so that's what this is going to kind of help illustrate through kind of an application type question. So suppose a certain state's annual rate of petroleum consumption over a 4-year period is constant and is given by the function f of t is equal to 1.2, where t is going to be measured from 0 to 4. T is in years, and f of t is in millions of barrels per year. In other words, this function right here, as stated above, is the rate of petroleum consumption. In other words, this is describing a rate of change, and more importantly, it's describing a constant rate of change, meaning that when I graph it, it's just going to be a constant horizontal line at 1.2, ranging from 0 to 4, because again, that will be a constant 1.2 million barrels per year. Now, when I shade in the area underneath this constant function from 0 to 4, notice that if I shade it underneath to the t-axis here, this area is a rectangle, meaning we can actually calculate this area, right? Because I have straight edges, this is a geometric shape. We do have a polygon here, and so I can use that to actually determine the area. Now, as we determine the area, one thing that I want you to kind of ask yourself is, what does this area actually represent? All right, because we are looking at an application type question, that means that every characteristic, every description has a meaning or has some kind of analysis, has some kind of description to the problem at hand. So when I calculate the area for this model, it needs to have something to do with this petroleum consumption, this barrel consumption per year. So let's go through and determine the area. All right, so I know the area of a rectangle is equal to height times width, or length times width, however you want to kind of look at it, base times height. So here my height is 1.2, and in terms of units, that's millions of barrels consumed per year here. That's my rate. Now I'm multiplying this by the width, which is years, so I'm going to add in that unit as well. And then using unit conversion, when I multiply these two values together and working with their units, I get years on the bottom and years up top, meaning that they'll cancel each other out. And so my answer will be 4.8, but not just 4.8, it tells me 4.8 millions of barrels. Million of barrels. In other words, it tells me the exact amount of consumption by the 4th year. And so this is what the area essentially represents, that if you find the area underneath a function to the x-axis and bounded by some value on the left and right, like here, right, we create some kind of shaded region, then what the area represents is a accumulation of a quantity, whatever that we're measuring. So like here, because we're measuring millions of barrels per year, if I find the area underneath that model, then that area represents the accumulation of the millions of barrels of petroleum. And so this is why the area question is such an important one to kind of find, because a lot of the times we know how things are changing, but I want to ultimately know how much are we accumulating? What would the total quantity be? And so I need to find the area for these very specific regions. But the issue, and this is what's going to be illustrated in the next problem, is that generally my rate of change is not constant. As you see here, let's assume this is the same type of problem. This function again models the rate of change per year. So in year one, the rate of change is somewhere in between 0.6 and 0.7, but year two, that rate of change is now dropped in terms of its usage, right? And a company won't use the same amount of petroleum every year, right? Same things in terms of if you want to even think about this year, think about the cost of gas, think about how much you're driving, right? Those rate of changes are variable, they're not fixed. And so when I have a situation like this, if I want to know how much barrels of petroleum have accumulated over these 4 years, to answer that question, I need to know the area underneath this curve to the t-axis. But because it's curved, I'm unable to find that exact area because we don't know how to find the area of an arc like this, right? I have formulas for specific polygons, right? I can find the area of a circle. I can find the area of a triangle. I can find, whoops, that's not a triangle. Why does it keep erasing it? Area of a triangle. I can find the area of a square or a rectangle. I can find the area of a pentagon. See if that'll work. Nope, give me a circle. Let's try it one more time. There we go. Any kind of shape like that when it has straight edges, right? A circle is the only thing that we can really do that's curved. So we need a method here to at least find an approximation or an estimate if I can't find the exact. And so this is the problem, right? How do we find the area underneath a curve? And so again, we won't be able to find the exact area. We will be able to come up with an approximation using one of these shapes, right? If I take my area and I can break it up into something I do have a formula for, then we can at least come up with an approximation that'll either be an underestimate or an above estimate or an overestimate for what we're trying to do. So here's the technique that we're essentially going to look at. And so here's some terminology, and I was kind of referring to this a little bit earlier. So when we want to approximate the area under a curve, we're looking for the area of the region bounded by the graph of a non-negative, so we're only talking about positive functions here, f, the x-axis, and the vertical lines from A to B, where A is always going to refer to this left-hand side, B is always going to refer to the right-hand side, so A is less than B. Then what we can say is that this area here, finding this area within these boundaries, is the area of the region under the graph of f on the interval from A to B. So whenever you hear me say, let's find the area underneath the curve, then from this point on, you can assume that we're finding just the area from the curve to the x-axis, and A and B represent these vertical walls, these boundaries to the region that we're looking for, right? If you were to calculate square footage of a room, right, you need 4 walls to calculate that square footage. You can't have a wall missing because then you wouldn't really have square footage, right? You'd be able to walk out. So you have to have boundaries, and we have to have at least 4 boundaries. 2 of those are always fixed. It's the function in the x-axis. The other 2 can be defined a little bit more in terms of A and B. All right, so in the next case here, I'm going to show you an example of how we develop the process to approximating. And this method is called using approximating rectangles. So we're going to choose to use rectangles in finding those areas because rectangles are pretty easy to solve. Like we did that again in the first example, right? It's just width times or height times width. Or length times width, or whatever dimensions you're kind of using to measure with. And so what we're going to do then is we're going to focus just on a fairly straightforward function, x squared, and I want to find the area of the region underneath that from 0 to 2. And I use Desmos here to actually graph that, so you can kind of see here's 0, 0, here is 2, and so I've got this arc here. And so it almost looks like a triangle would be a really good approximation, but notice how if I drew a straight line there, and I can do that, my triangle region wouldn't be great. And then if I was to try and go through and draw more triangles, it's not as efficient, and the formula is also a little worse. So that's why we're just going to do rectangles. And this is kind of the general theory, general property, general technique. They call these Riemann sums. We're only going to really do this in terms of coming up with the main definition, and then that's all we're going to do, just because of the sake of time and being at the end of the semester. So this is what my goal here is to come figure out what is the area of this region. To start, we're just going to kind of build into this. So the very first thing that I'm going to do is use just one rectangle. So let's see, let me make sure I should have plenty of space. Okay, so we're just going to use one rectangle. And as I go through and do this, I'm going to let the height be determined by the right endpoint on this interval from 0 to 2. All right, so from 0 to 2, I'm going to go up to my function. I'm going to use a green color here. And I'm going to draw a box. And this is going to be just an approximation. As you can tell, it's going to be a pretty poor approximation because the area of this box is only like twice as much as the actual area of my figure that I care for. All right, and so let's go through and figure out what the area of this box is. So the width of this box is determined by doing 2 minus 0, the overall interval, divided by 1. So this would be 2 over 1, or 2 units. And then the height is determined by, again, the right endpoint. So the interval I was looking at was from specifically 0 to 2. And so I'm going to use this value here to go up and draw my height. And then I can go through and calculate the area for my approximation, which would be f of 2, so 2 squared, times my width of 2 units. So again, f of 2 just means I want to plug this in to x squared. That's the function we have. And then I would get 4 times 2, which is 8 square units for my area. Again, we know that this would be an over approximation, right? This is a pretty bad approximation just to do one rectangle because I have so much empty space up here, right, that I'm calculating that's not actually part of my final solution, or at least the final area. So what we need to do then is come up with a better approximation. Well, if one rectangle is really, really bad, what if we were to do 2 rectangles instead? All right, and so that's what this next little part is going to kind of build into. So let's take my overall region from 0 to 2, and let's create 2 rectangles of equal width. All right, and so let's go through and calculate what that would be. So my overall interval, again, is from 2 to 0. So I subtract those 2 to figure out that length. And then I want to divide this time into 2 rectangles, which would give me 2 over 2. Each rectangle would only be now 1 unit in length. So if I'm starting at 0, then use green again. If I'm starting at 0, the next boundary marker for my rectangle would be here at 1. And then the next one again would be at 2. So here are my strips. And then I'm going to let the height be determined again by the right-hand side of each of these little mini intervals. So for the first rectangle, I would go here to 1, go up to the curve, and then that's how I would draw my height. For the second rectangle, I would go up to 2, and then I would draw my height. And so now I've got 2 approximating rectangles. And notice, unlike when we did the prior one where we were only using 1, I'm now not including this area here. So this means this will be a better approximation. It's still not a good one, right? This is still going to be a fairly large overestimate. You can see how much more the rectangle goes over the graph. But nonetheless, it is a better approximation. So I want to go through and find these areas here. Now, the way that I'm going to kind of break it down is I'm going to call this area 1, and I'm going to call this area 2, and then we're just going to add those 2 results together. So my area 1 is found by doing f of 1, because that's how we drew the height, right? I went to an x value of 1, and then I went up to the function. And this would be multiplied by the width, which is 1 unit. Well, f of 1 is 1 squared, so just 1 times 1. So I get 1 square unit for the first area. Area 2 is found by doing f of 2 times 1, which would be 4 times 1, which is 4 square units. So then my approximation then for the area underneath x squared from 0 to 2 would now be 4 plus 1, or 5 square units, which notice is very different from my approximation with 1. We're 3 square units less. And so we're getting closer to the actual area that's shaded in blue. But again, the issue here and the problem is that I still have all of this excess area above my curve here. So I need to find a better approximation. Well, to find a better one, we just need to increase the number of rectangles. This time, let's do 4 rectangles. So let's double the amount that we're going to use. All right, so because I'm doing 4 rectangles, and again, I want them to be, and this says 2, but I really want this to be 4. I want them to be of equal width, so it makes my calculations a little bit easier. And then the height of each rectangle, again, is going to be given by the function value at the right endpoint for each little interval. All right, and so the width, I would go through. My overall interval was 2 minus 0. And this time I'm going to break this up into 4 equal pieces. So I'm going to divide by 4. So 2 divided by 4 is 1/2, or 0.5. So this is the width of each rectangle. So I can come now to my graph, and let's break it up into 4 equal strips. So starting at 0, the next strip would end, or the first strip would end at 0.5. The next strip would end at 1. The next strip would end at 1.5, and then 2. So notice I've created 4 different strips, and then going on the right-hand side of these to the curve, drawing across, there's 1, there's 2. It's almost like I'm creating stairs. There's 3, and here's 4. And I want to find these areas here. Again, notice I'm still going to get an overestimate, right? Those rectangles are still taller than the actual curve, but I'm starting to minimize how much over I am. So my approximation should be better, and my guess is that it's going to be smaller than what we got in the previous step, which was 5. All right, so to go through and do this, I'm going to call this A1, A2, A3, and A4. So A1, my height is f of 0.5. My width is 0.5. F of 0.5, so if you were to plug 0.5 into x squared, you would get 0.25 times 0.5. I get 0.125 square units. That's the first rectangle. For the second rectangle, the height is determined by the right endpoint, which would be 1. And I'm going to multiply this by the width, which is 0.5. So I get 1 squared times 0.5, which is just 0.5. Excuse me. The next rectangle, the height is determined by f of 1.5. So you can see how everything in the parentheses is essentially going up 0.5. And then I'm going to multiply this by the width, which is 0.5. And so I would get f of 1.5, so 1.5 squared is 2.25 times 0.5, and I get 1.125. For the fourth rectangle, the height is determined by 2, so I do f of 2, and then I multiply this by the width, which is 0.5. So 2 squared is 4 times 0.5, and I get 2. So this means that the total area, my total approximation here, which we know is still going to be an overestimate, I'm going to go through and add each one of these final results that we got, and I get 3.75 square units. So notice that our approximation here isn't as drastic of a change when we've increased to 4 rectangles from 2, as it was going from 1 rectangle to 2 rectangles. So if I do compare 1 to 4, though, it's a massive change. Roughly almost half of what we started with, a little bit over half, when we did 1 rectangle. So 4 rectangles is way better than just 1. All right, well, what would be better than 4? Because again, I've got some overestimates here. Well, let's double the amount of rectangles. So well, let's go to 8 rectangles. Again, it looks like I was copying and pasting these directions, so I forgot to put in there. So this time, let's do 8 approximating rectangles and see what we get. So the width of each rectangle, again, my overall interval is from 0 to 2, so that's a length of 2. I'm going to divide this by 8 because I want 8 equal rectangle widths. So this would be 2 over 8, or 1/4. I'm going to use the decimal, which is 0.25. So if I come over to my graph, I'm going to draw my strips. So starting at 0, the next strip would be at 0.25, so halfway. So here, really, really tiny rectangle. The next one would be another 0.25, so 0.5. Then the next one would be 0.75. Then 1. Then 1.5. Or sorry, 1.25. To 1.5. To 1.75. and then 2. All right, so just kind of freehanding. So then kind of shading these in. I want to find these areas. Again, notice that the bit of the rectangles that is over the curve now is a lot smaller than when we did just 4. So this answer that we get here should be a much better approximation and closer to the actual area that's underneath. So I'll call this A1, A2, A3, A4, A5, 6, 7, A8. All right, so I want to go through. Let's find the area for 1. So this means the height was determined by 0.25. So notice this is essentially starting with the width, and that's because we're starting at 0. Multiplying by the width, which is 0.25. Using a calculator here, I get 0.015625 square units. For the second rectangle, I would do f of 0.5 times 0.25. Again, using a calculator, 0.0625. A3, I would do f of 0.75. You can kind of see how the increments here are going up by the width times 0.25 would give me 0.140625. My fourth strip would be f of 1 times 0.25. Well, this would be 0.25. I like that one. The fifth strip would be f of 1.25 times 0.25. This would give you 0.390625. Almost done here. The sixth rectangle, the height is f of 1.5. The width is 0.25. Multiplying this out, you would get 0.5625. The seventh one is found by doing f of 1.75 times a quarter. This would give you 0.76565. And then finally, the last approximating rectangle, plugging in f of 2 is my height times a quarter, and this would give you 1 square unit. So now totaling all of these, my total area, my approximation here, which again is an overestimate. We're essentially finding a ceiling and now we're lowering it by increasing the number of rectangles. Adding all of these values up, I get 3.1875 square units. And this would be for using 8 rectangles. Now you can see how the work is very, very, very tedious. And so we want to try and come up with a faster approach to this. That faster approach is, if you're paying close attention to the pattern, there is essentially a formula for this. Now this method again is called right endpoint rectangles. So if you were to always use the right endpoint for each little interval, for each little strip, then what I can actually do is I'm always finding the function value, but doing a plus, so my starting left-hand side, plus the width. Now the width is actually abbreviated or notated as delta x, my change in x, right? How much are we actually changing to inside each strip? And so I would call this essentially delta x, and then I'm going to use the variable n here just to represent the number. So if you want the first strip, n would be 1, and then my a is 0, so I would do 0 plus the change, which is 0.25, and this would give me f of 0.25, and you'll see how that was used in the first strip when n was equal to 1. If n is 2, I would add another 0.25, n is 3, another 0.25, etc. So that's kind of the pattern. Now this kind of crazy expression right here is modeling just the height of each strip. I would then need to multiply by the width, which again is given by delta x. And then this would essentially be the expression for each individual area. So because I want to add it all up, hopefully you remember sigma notation. I'm essentially saying n is equal to 1, and I want to go all the way to 8. So this n here essentially represents my index. So if I want the first rectangle, n is 1, second rectangle, n is 2. And as you go through and calculate each one, then sigma says to add it all together to give me this. All right, and so this is kind of the formula for this. I didn't put this in the lesson notes for this video, but I wanted to go ahead and write it right here just to kind of show you, because I actually used this to, and used a graphing calculator to say, okay, well, what would happen if we were to continue doubling the number of rectangles and kind of looking at the trend of the area. In other words, because we know that this is a finite area, if I continue to increase the number of rectangles, then we should continue to approach the actual area, right? The approximation should start trending to a very specific value, and we can kind of see that already by looking back at our answers again. So in other words, when we started with one rectangle, I got an area approximation of 8. When I doubled that to 2, we got an answer of 5, so you can see the decrease there. When I doubled that to 4, we got 3.75, so still less than 5, so we're still dropping. But when I doubled this and I went to 8, notice that the answer was 3.1875. In other words, this whole number here essentially became fixed, right? The decrease, we're getting smaller and smaller in terms of the change as I'm increasing. So I'm getting closer to my answer is essentially what that means. I'm trying to think of like the best way to kind of say it. How I kind of picture it is in words. When you're comparing values, when you see a lot of drastic change between each entry, that means you're pretty far off from the actual answer. But as that difference between each entry gets smaller and smaller, it means we're getting closer and closer to the actual answer. And so what I have here is a table where n, again, represents the number of rectangles that we want to use. And using the right endpoint, you can kind of see the values that we would get for the area. So for 8, we got 3.1875. If I double that, my approximation drops below 3, but it only drops by about 0.2, right? And then again, this now would drop a little bit less than 0.2 if I doubled it to 32 rectangles. To 64, see how 2.79 goes to 2.72. So again, I'm starting to get some fixated decimal values, decimal placeholders. If I go to 100, this is 2.7068. To 1,000, 2.67. To 100,000, 2.667. And if we went to then a million, 100 million, a billion, a trillion, your calculator would literally break. But the answer is going to be 2.6666666666666, which represents 2 2/3 or 8/3. This represents the actual exact area under the curve x squared from 0 to 2. So in other words, what we were able to do here is using this approximation idea, we just found the exact area. But the way we had to do it is that we had to let the number of rectangles increase, and they have to continue to increase essentially to infinity. So if we let n go to infinity, which represents the number of rectangles, if we let it increase without bound, then our approximations have a limit, right? My approximations will approach some boundary point, and that boundary point represents the exact area. So we can find and we can answer this area question. How do we find the area underneath an arc? Well, we have to use a bunch of approximating rectangles. Now, this method, though, is very, very inefficient because, I mean, just look at how many rectangles we would really have to do to get really, really close to the actual answer. All right, we would need to do something like greater, probably like 1 million rectangles just to see it. And, you know, before calculators and before computers, how would you do this? Because again, this is stuff that was invented, or not invented, but it was kind of discovered and created by mathematicians, you know, Isaac Newton. It was used by this guy named Leibniz to a bunch of even mathematicians before that. So what kind of approaches did they do here? Now, Leibniz came up with this new notation to represent this entire process, and that's what you see here, which was at the bottom of your screen. We define this limitation, we define this process of a limit, letting n go to infinity here, the number of rectangles. This is called the definite integral, and this is where we're going to mostly be focused on for the remainder of the video, and we're almost done, as well as what your actual assessment would cover and your very last video will cover. Now, what a definite integral is it's notated as this little s symbol. That little s symbol is the integral symbol, and it stands for sum, right? It's an elongated S. Sum, sigma, right? We saw that up here because we're adding a bunch of approximating rectangles. So that's what that stands for. The A and the B refer to a lower limit and the upper limit. In other words, it's your left and right boundary, right? I want to find the area. I want to add up all of the approximating rectangles from 0 to 2. So A would be 0, B would be 2. Now, f of x, remember, is calculating the height. This dx, delta x, that stands for the width. So notice how this expression in here is really just calculating the area of a rectangle. But it's an infinite number of rectangles. And so that's why we have this expression just listed in general of f of x dx. So I would be calculating a bunch of little infinitely small in width rectangles from A to B. And if I do that, letting that number n go to infinity, I would find a finite area, and that finite area is represented as this integral symbol right here. So here's the geometric representation, or the interpretation. So if f is continuous, so right now no vertical asymptotes, no breaks or anything like that, from A to B, then what this definite integral represents is it is equal to the exact area between the function and the x-axis. So what I'm going to go ahead and do now, without going into a ton of detail, is we're going to let my function be negative, right? So it can dip below the x-axis. Now, when that occurs, essentially region 1 here would be a positive area, but region 2 would be represented as negative. The best way to kind of think about it is let the x-axis be sea level, then you can go in elevation below sea level, right? It's a negative elevation, and that's what can happen here with area. Anything that dips below the x-axis is just represented as a negative area because its height or its y value is negative. So when you were to calculate it, that's what you would get. So one thing that's really, really interesting about the definite integral is that the definite integral is just going to add up all of the areas. So if R2 is negative, then the integral would be equal to this expression down here on the bottom, where I would do area of region 1 minus the area of region 2 plus the area of region 3. In other words, the definite integral calculates the net area, right? If something dips below, it stays negative. It's not finding total area, right? It's going to treat that as negative space when you do a definite integral. All right, and that's just something I wanted to let you know. It's not something that we're going to worry about too much here because we're not going to dive into that mathematical realm too much. Okay, so let's take a look at an example then. So, and this will be where we end. I've got some properties, I think, after this, but then we'll be done. So example 1, so evaluate the definite integrals. Looks like the G got erased there. And below, so the integral from 0 to 3 of 2x dx. Now remember that the definite integral is just asking you to find the net area underneath 2x from 0 to 3. So I've got 2x graphed here. It's what this red curve is. And I've got 0 marked here. I've got 3 marked here. And I want to find this region here underneath the curve to the x-axis. Now, this region, I don't need to use approximating rectangles because we know how to find the area of this. This is a triangle. So that means the area can be found by doing 1/2 base times height. The base here is 3. The height is determined by plugging 3 into the function. So we could count it because it's on a graph, or we could just do 2 times 3, which is 6. Sorry, I kind of slipped on that. That was 3. And so when I multiply all this together, 3 times 6 is 18. Multiplied by 1/2, I get 9. So this means that the answer to that definite integral from 0 to 3 of 2x dx is 9. All right, the solution to a definite integral is a number because we're finding the area. Excuse me. So let's take a look at B. So B is the integral from 1 to 2 of 1 plus 3x dx. And so if I was to graph 1 plus 3x and then list the boundary points from 1 to 2, I get this shape, this shaded region here, which is a trapezoid. The area of a trapezoid is given by 1/2 sum the bases times the height. The height represents the width of this. In this case, yeah, so we'll do it that way. because the bases are determined by the parallel sides, which are here. I'll call this little base, and this is big base. So if I want to find the area, this would be 1/2. Plug 2 in. I would get a height of 1, 2, 3, 4, 5, 6, 7, plus a height of 4. And the height here would be the width. This is my h, and that's 1. Trapezoids are kind of weird. Luckily, again, we don't have to worry about it too much. Multiplying all this stuff out, this would give me 5.5 square units. And this right here is the answer to the definite integral from 1 to 2 of 1 plus 3x dx. This answer is 5.5. Again, a definite integral represents finding the exact area of a shaded region, and we just did that by using a trapezoid formula. All right, and part C, we have it from -1 to 3, so my boundaries can be negative. And I want to go from -1 to 3 and find the area underneath 2 minus 5x. So I have that graphed here. This time notice that there are two different regions, region 1 and region 2. Region 2 is going to be negative, and I'll show you how this comes up naturally, but we'll go through and kind of work this out. So region 1, because again that this is a triangle, its area is found by doing 1/2 base times height. Now my base here, going from here to here, is 2/5. And I actually think I calculated that wrong. All right, so the base is 1 plus 2/5. So it's actually going to be 7/5. I wrote that wrong in my notes. Okay, so the base is 7/5. The height is 7. And so for region 1, I would get 49/10 is my square footage. All right, or square units. For the second region, this would be 1/2. The base would be 1, 2, and 3/5, which is 13/5. And the height here would be going down to -12. And I would use that value for -12. So notice how this overall area that I would get is going to be negative. And this would come out to be 6, so -78/5 square units. This means that the integral from -1 to 3 for this function, which was 2 minus 5x, is equal to 49/10 minus 78/5. And so adding this in, finding a common denominator times 2 times 2, that'd be 156. So 49 minus 156 is 97, so -97/10. Hopefully I did that math right. And so this would be my final answer to the definite integral. There's my area. Overall, it's negative. Makes sense because the region that's underneath the x-axis is larger, so this means the net area should be negative. All right, last but not least, for D, we are finding, whoops, I actually left the work up. This again is a trapezoid. All right, for this function 3 plus 1/2 x. I want to find the shaded region in between -3 to -2. So this would be 1/2 base times height, but because it's a trapezoid, it's base plus little base. And in this case, the big base is 2, the little base is 1.5. I labeled it backwards. The width here is 1, so that's my height. And so multiplying that out, I'd get 1.75. All right, so for when we evaluate, when we're looking for a definite integral, again, we are finding the exact area. And if the functions that we're looking at have straight edges, then we can find the exact area by using our normal formulas, right? So it represents that. All right, now let's take a look at some properties. We're just going to kind of glance through these, and then we'll do the closing for this video. All right, so some properties. So let f and g be integrable functions. Then if I want to integrate, so if I want to find the definite integral for f of x from a to a, right? So notice how my lower limit and my upper limit are the same. And if I want to find that area is going to be 0. Now this should make sense because if I look at a graph here, and I was just to draw some kind of arbitrary function, so it doesn't even matter if it's straight, and I say, okay, I want to find the area from here to here, there's nothing shaded, right? There's no span there. There's no scan. There's literally no area there. So that answer will always be 0. So for any of the above problems, say for example, when I showed you D here, if this problem instead was -3, then we could just say that the answer was 0 immediately. That would be done because -3 to -3, that answer is just 0. All right, now this one's going to be kind of interesting, and I'm not going to prove it, but I'm going to leave this here for you, which is if we are integrating from A to B, if I want to swap the bounds, we can, but if I swap them, it negates the overall area, right? It changes its sign. So you are allowed to swap the bounds of a definite integral as long as you negate the original integral, right? And the reason really stems from how we calculate the width. So if you remember when we were doing the delta x for the approximating rectangles, I was essentially calculating it as b minus a over n, right? The right minus the left and divide it by the number of times that I want to do it. But if I swap what's considered right and left, if I swap what's considered up and down, I'm changing my point of reference, so it'd be a minus b over n. The difference here is a sign. The difference is an extra negative, and so that's kind of the idea here, is that it negates the original problem. All right, now the third property says, just like when we were to derive a function, if I have a function multiplied by a constant, I can bring that constant outside the integral, right? So we can simplify a problem. So if I had an integral from 0 to 3 for like 4x dx, instead of having to work with something with a slope of 4, I can bring that 4 to the outside. And so I could find the area under just x, which would be easier to work with, find that area from 0 to 3, and then just quadruple it, right? I can post multiply by 4. Very, very, very similar to how we worked with derivatives. Again, similar to derivatives, I can add or subtract on the inside with functions, which means I can actually break it up into two separate integrals. So that means, again, in the problems that we were looking at beforehand, so say, for example, this one again right here, we had the integral from -3 to 2 for 3 plus 1/2 x dx. I could actually break this down according to the third and fourth property as the integral from -3 to 2 of just 3 plus the integral from -3 to 2 of 1/2 x. So again, it makes my drawings a little bit easier. And then I can even bring out the 1/2 in the second one to make my function even a little bit more easier to find, which is just x dx. Now, what's kind of interesting about this is I'm going to go back to this line here, the first one that I did. This first integral right here is the box or the rectangle created right here at 3. The second integral is actually finding the area of this triangle, which is 1/2 x with a width of 1. So just something to kind of point out here, that if you were to break a trapezoid up into a triangle and a rectangle, what you're literally doing to the original integral is breaking it up into the individual pieces. So you're actually already using that property. All right, the final one says that if you want to find the area from A to B, that is the same thing as finding the area from A to C, and then adding that with C to B. This is called the traversal property. Think about it like a road map. Essentially, probably a little bit easier too to think about it from right to left. If you're finding the area from A to C, and then the area from C to B, and adding that together, then this is the same thing as just doing it from A to B, right? You skip the middleman. Like why break it up? Why not just go ahead and find the total area? Because they're sitting literally side by side. And so these properties are going to be helpful. So they're ones that you're going to use a lot if you retake calculus or take Cal 2 at some point, even business Cal again. And so for closure, what I kind of want to highlight again is what a definite integral is, right? So if I have a definite integral and I want to integrate from A to B for a function, f of x, what this is referring to geometrically is the exact area under the curve f of x from A to B. So if I was to draw, again, just kind of an arbitrary function for f, say this is f of x, and then I have, here's A, and here's B, what that integral represents is this shaded area right here. And it represents the exact area. Now, from our examples, I could not find the exact area of this. What I would have to go through and do is use approximating rectangles. I would have to break this up into multiple rectangles and then let that multiple rectangles grow again and then grow again and then grow again. Let that number go all the way out to infinity and evaluate that limit, evaluate that approximation, and then I would have the solution. Now, that is not very, very efficient. And so therefore, we still haven't fully answered the area problem, right? We know that we can use these approximating rectangles to get there, but again, it's not easy to do. The mathematics gets very, very, very difficult. So in the next video, what we'll get into is that there's something really, really interesting when we're looking at definite integrals in these exact areas. And there's some kind of relationship to a derivative. And so we're going to start looking at that, and that'll be our final video, and then you'll have your final assessment. So thanks for watching. Again, let me know if you have any questions, and I look forward to hearing from you.